Hi guys, long time no see, PhD, sorry. Got something really cool for you, though, this video. Look at it, it's a big long one. A couple of weeks ago I got to go to the University of Reading to give a talk on my research and also to film a bunch of experiments. So I've got a couple of videos coming out from this trip. In this one, I'm talking with newly Dr Graham Marlton, who has his PhD in meteorology, and we're launching a weather balloon, or radiosonde. So this is basically a bunch of scientific instruments that you strap together, you put it on a balloon and you let it go, and then it radios the information back to you. It's called a radiosonde because, radio, and then sonde is the French for sensor, I think. And it's actually a part of modern meteorology. It sounds kind of archaic, and I bring Graham up on this, but it's actually really, really modern, and a surprising number of these. You're not going to believe how many of these are launched every single day. So, the main part of this video is me getting to sit down with somebody who really knows their stuff, a PhD in the field, and we look at the data that's coming from this thing in real time as it goes through the atmosphere, and we're analysing what's happening when it enters clouds, when it enters the jet stream, when it enters into the stratosphere, and all that kind of stuff. And I would think it was really, really cool to be able to sit with an expert and, get the inside scoop on this stuff. So I filmed it all. I really hope you find this interesting. Give it a shot, and I'll be back a little bit in the course of this video to explain a few terms that we kind of don't define because we're a bunch of sort of meteorology nerds. But over to past Graham and Simon to talk about what we're doing in the experiment.
So today we're going to be launching a radiosonde on a weather balloon, and these radiosondes measure pressure, temperature, humidity, and we can also find out the wind speed from these in the atmosphere. So we're going to launch one of them, but we're going to have a little bit of a twist on it today. We're going to be adding some special sensors so we can look at turbulence, solar radiation, and something which gives a bit of information about space weather.
Now, isn't this all a bit old-fashioned? Why aren't we doing this through satellites?
Well, one of the problems is with satellites is you can only look at certain bits of the atmosphere with satellites. So you can look at the top of clouds, you can look at the land surface, but if you're underneath a cloud, how do you know what the temperature is going to be underneath the cloud? Jet streams, they're clear air, and so it's quite hard to find out what the wind speed's doing. So we need to launch the radiosonde to find out all the other bits that the satellites can't look at.
So this is still relevant. This is modern meteorological science.
Yeah, this is very modern. Thousands of these are launched around the globe each day, and they form the backbone of building up the picture which the forecasters then use to initialise their models. So this is the RS92 radiosonde part, and we've got on this metal strip here, we've got the two humidity sensors, and the reason we have two humidity sensors on the radiosonde is as you get high up into the atmosphere, temperatures get very cold, and so it starts going quite hard to measure humidity. So one of the sensors is heated up to de-ice it, while the other one makes measurements, and then every 30 seconds the sensors switch over and the other one's red, so we can maintain good measurements of humidity. This small thin wire here is a capacitive temperature sensor, which provides the temperature sensor. Inside the radiosonde there is a pressure sensor, so we can derive the radiosonde's height, and this rather fashionable spiralling device is the GPS, and from the GPS position we can work out the radiosonde's speed. What isn't on a normal radiosonde is this box here. Now here at the University of Reading we've developed a system where we can add additional sensors to a radiosonde. So the first thing to look at is there's a small photodiode in the top here, and we can use that to measure the solar radiation as the balloon goes up to the atmosphere. So on a day like today, if we do go through a low cloud, we'll be able to see it because the variability from the solar radiation sensor will stop. Inside we've got an accelerometer, which is very similar to that of which is in most smartphones or Nintendo Wii's, and that can measure the turbulence as the balloon flies up through the atmosphere. If the balloon's perturbed by turbulence, the radiosonde will swing around underneath. The more the radiosonde swings, the more turbulence it's in, so we can get some interesting information about turbulence. The majority of this box is taken up with a Geiger counter, so the sun is often going through different solar cycles, and its cycles can affect how many cosmic rays reach into the atmosphere. So at about a height of 12 to 14 kilometres, we should be able to see a peak in cosmic rays which are detected by the two Geiger tubes which are in here. And from that we can learn information about how the sun's solar cycle is affecting our atmosphere.
Just like to point out, all the equipment that Graham was talking about, like everything in total, it costs like 500 quid to do one of these launches. So thank you, meteorology department at Reading so much for letting me do this. It was really, really cool. I hope you guys see that money. Sorry for interrupting, and I'll pass you back to Graham in the past, who's filling up the balloon.
The balloon is just made of rubber and latex, so not like the rubber in a party balloon. It's just got a bit more stretch and a bit more give than a normal party balloon.
And presumably it gets a lot bigger the higher you go.
Yeah, so this one should be about 5 metres wide for a time it bursts, so it usually gets about 3 times as big.
And that's what limits the height that you get to?
Yeah, there's 2 factors: how much gas you put in. If you put just enough gas to get the thing to lift, you can get higher because the balloon doesn't have to expand as big, but then you can't lift as much. And then other things, like if you send it up very slowly, you then run out of battery on the radiosonde.
Is that yet more electrical tape?
Yeah. Okay, when you're ready.
Ready when you are.
So we've just running. We just launched the radiosonde, so it's been in flight for maybe just about a minute now. We're starting to get the temperature profile in red come in. So it's been about 18 degrees at the surface, and as we probably head up into the first kilometre, it's already dropping to about 10 degrees C. Humidity is about 65%. The wind direction's northwest, and the wind speed's quite slow. It's about 3 metres a second at the minute, which is
Very calm.
very calm. It's a great launch. Nothing out of the ordinary at the minute. And also, as we're going up, the solar radiation is starting to get stronger. So when you fly up through the atmosphere, we have what we call a top of atmosphere solar radiation value, and we also have down below, so things like water vapour, very high level ice clouds, cause the value to lower. So the green line here is pressure. So we started at about just over 1,000 hectopascals, and that will decrease with an exponential trend as we head up through the atmosphere. So something that I'm just going to draw your attention to here now is we see here the relative humidity has gone to near 100%, and there's an actual dip in the temperature sensor. So we can actually learn a lot about this because there's a little inversion at the cloud edge.
So that's just entered a cloud.
So it's just entered a cloud and come out of a cloud at the same time. So we can see that it was a very big jump here. But because there's a little inversion here, we can say, well, actually, the radiosonde's gone through the cloud, and it's actually got some moisture on the instrument. As the moisture's evaporated off, you get some latent heating, so it actually causes the temperature gauge to drop really quickly for maybe like a few seconds as the water evaporates off.
Hi, me again. Sorry, I'm not going to do this very often, trust me. I just needed to point out something here. We're talking about inversions. What we mean here is temperature inversions. So normally in the atmosphere, the troposphere, which is the bit that we live in, the temperature decreases with altitude. Sometimes, though, it increases with altitude, and some weird stuff can happen there, interesting meteorology. That increase in altitude of temperature is called an inversion. So that's what we're talking about here, just to clear that one up.
But from solar radiation point of view, the values are a lot higher than they were when I started talking 5 or 10 minutes ago.
So you're going higher up through the atmosphere, less of it's being filtered out by
and the fact we've gone through a cloud as well.
And we're just about to hit freezing. Actually, it's just started increasing.
Yeah.
So is that another temperature inversion?
Yes, this is temperature inversion. So I suspect what's happening here is we've got a cloud, and so it's not a perfect thing. So maybe it went into a cloud, maybe dived out the cloud, went back into the cloud. Because if we would have looked out today, they're all a bit cumulusy. So there's kind of pretty random structure to them. But what we get here is top of an inversion, and I'd say given the height we're about to get to, which is about 1,700 meters, that's probably the top of what we call the boundary layer. So between the structure of the atmosphere is such that we have maybe in the first 2 kilometers a boundary layer, and that's basically a part of the atmosphere which reacts to the Earth's surface. So you get turbulence from flow over buildings, you get heating of the atmosphere due to convection, and this all happens in the first 2 kilometers, and then you you reach a bit, and it's often marked with a temperature inversion. So this is actually quite a big temperature inversion. It's surprisingly big temperature inversion. We'll have this inversion, and as data comes in, it should start heading off like that.
So no two balloon launches are the same?
Oh no, absolutely not. So in part of my PhD project, we did some launches down in Aberystwyth in West Wales. The main aim was to fly turbulence sensors, which is what's one of the sensors we're flying today. And you found you do one launch, say at midday. So, it's not really much going on. Well, this is a bit disappointing. And then you do one 2 hours later, and the turbulence has expanded. The region of the atmosphere, it feels, has expanded.
Okay, so the big mystery here, the big question in the room is what on earth is going on with humidity? So read that graph for me. What can you tell me?
So what I'm seeing here is we're in the boundary layer here, and we've got some clouds at the top of the boundary layer. So given that's about a kilometre, we can say, right, there's clouds at a kilometre. And we come out the cloud, and we've gone through this inversion bit in the temperature. And how I'm reading that is maybe these clouds we're seeing today are in the top of the boundary layer. And what's happened here is maybe we're encountering a little bit more cloud. We'll have a look outside and you can see it's kind of quite fractal and quite spherified. And as we enter this bit of the atmosphere here, this is more of the background free troposphere. So this is just moisture that's been transported in the troposphere. And the humidity is a very variable thing. So from now I could say this bit of the atmosphere is looking like a typical radiosonde descent. But if it gets very dry, we may have to think about other things like a tropopause fault happening. One thing we've learned about doing maybe 50 or 60 of these launches is never say never to anything. You always never know what you're going to find. Right, so what we've got here is just a plot of the radiosonde's trajectory. So in the centre here is where we've launched from the Atmospheric Observatory here in Reading, and we've slowly started heading out. So the radiosonde's probably about 6 kilometres away from here, and it's heading southeast of us. So we're just going to head south over Guildford, and
it's not that far considering how long we've launched for. How many minutes is that now?
So we're in about 12 minutes. We've been in flight for.
But would you expect it to suddenly shoot away?
Well,
into the stratosphere, say.
We're just approaching 500 hectopascals. So I checked the weather forecast yesterday, and there should be a light jet, so we can see the actual speeds picked up to about 70 meters a second, which is about 30 miles an hour. So in the jet, given the forecast yesterday, I'm expecting 50 to 60 miles an hour. So expect to see this value actually increase in the next 4 or 5 minutes. Mm-hmm. When we encounter this jet stream, we're probably going to encounter a little bit of turbulence, which you should be able to pick up with the accelerometer. So that's what's happening. So
where are you anticipating that it's... Because eventually the balloon is going to pop.
Yeah.
Where do you think it's going to come down?
So I reckon it'll either come down the British Channel.
Well, it's a serious question now. How many of these do you launch? I mean, are they starting to clutter up the world's oceans?
So they launch about 1,000 of these a day across the globe. And so the Met Office, they definitely launch 2 down at Camborne in Cornwall and 2 up in Lerwick in Scotland. And they launch 2 a day, and then there's various automated sonde sites around the country which launch 2 times a day and 4 times a day if need be. So the UK probably launches, I know it's supposed to be about 10 to 20 a day. So one's launched around here, most of them end in the sea. So say in the States, they just land in farmers' land, and they just say, if you find it, just put it in the bin for us. When I was showing you earlier, the sensors are so delicate. If they've crashed down in a field, it's not worth repairing them again.
Which is why I've not put a camera on it, because I'm not breaking my GoPro.
Yeah,
sorry.
Absolutely. Oh no. Thank you for not putting a camera on it, 'cause it complicates it. So as you see, actually, in time we've been talking, the wind speeds now, we're up at 20 meters a second. So that's now 40 miles an hour. And so we're actually, when we started talking, we were at 6 kilometers. We're now at 9. So it's actually really started picking up a bit of speed now since we've reached the mid-troposphere. And so
this is the jet stream.
This is the jet stream. So the most intense jet stream we've had on record was about 223 miles an hour, and this radiosonde actually made it to Belgium.
Wow.
And then the radio transmitter wasn't powerful enough to relay any more information. So
it probably went even further.
So it probably went even further than that, but that's the departmental record. Probably what I'd say here is, maybe here we've encountered, so if you look up there, there's kind of a haze in the air, and that could be maybe just quite a thin, high layer ice cloud, which we've encountered there. Over there, we can see we've got these, so it's like what we call altocumulus, and these are very high level clouds in the background. And if you see, there's maybe a wave pattern in there, and that could be due to maybe a little disturbance in the atmosphere, maybe to do with the jet stream that we saw in the radiosonde launch, just causing a very small wavelet effect. You see there's a few inversions that went with it. The speed of the sonde's now up to about 35 meters a second, so it's 70 miles an hour. So it's actually going a little bit quicker than I thought it would. So if we actually look here on the channel 4 auxiliary, this number's moving around quite a lot. So we now know that's in turbulence. So we're actually detecting turbulence now.
So does this mean we're getting towards the top? Also looking at the pressure, we're getting towards the top of the troposphere now.
Last time I interrupt. Really sorry. Don't mean to ruin the flow. So here, what we're talking about is we're about to enter into the layer of the atmosphere that I researched, the stratosphere. Now, for those of you that haven't seen my other videos, just going to give you a primer really quick. The atmosphere is like ogres, like onions. It's divided into layers. So you have the bottom layer, which is the troposphere that we live in, and that's from like sort of the surface to about 10 kilometers in height, though it does vary in altitude depending on where you are on the Earth. And then between 10 kilometers and 50 kilometers, you've got the stratosphere, which is, as I say, where I do my research. From 50 kilometers to about 80, you've got the mesosphere, but we're not talking about that in this video. Now, the troposphere, as I said earlier, has that thing where temperature decreases as you get higher. In the stratosphere, to begin with, it actually stays kind of constant temperature as you get higher, and then it actually increases as you get higher. And those two layers, troposphere and stratosphere, have really different dynamics going on. They look totally different. And the boundary between them, which we talk about in this next little bit, is called the tropopause. And we're here trying to guess where the tropopause is going to be. I'll show myself out.
A game I often like playing is guess the height of the the tropopause. So, do you have anything? Do you have a guess?
My default guess is 10 kilometers.
10 kilometers.
Which is, we're at 9 now.
Yeah, I'm going to say I reckon about 11 today, but I could be wrong. Yeah. So it's minus 36 up there, which is pretty cold. So
must be getting towards the tropopause.
Yeah,
because we're not in winter. So
we're not in winter. So the temperature tropopause is about minus 50, minus 60. So I'm feeling probably an 11 kilometre-ish tropopause. Kind of entered quite a smooth, temperature-wise, quite a smooth part of the atmosphere. The other indicator of us going to tropopause is the humidity will drop to almost zero.
Nothing,
almost zero.
And that's because you can't convect the moisture into the stratosphere.
Yeah, and it's so cold up there.
Everything will turn to ice.
And it turned to ice, and so the actual tropopause provides a layer. It's just a change between buoyancies. And so when you see the big thunderstorms you get over the US, it all fans out in an anvil, and that's because it can't get there. But in case if you've got very strong convection, it can actually punch through and you get a little top bit. But that's one of the few ways you can get moisture into the stratosphere.
So when will we know we've hit the stratosphere?
We'll get quite a sharp change in direction, so the temperature won't increase with height anymore. Or sometimes it can just kind of slowly bend round. Sometimes I refer to it as a lazy tropopause when it's a bit ill-defined. But yeah, we're still in turbulence by the looks of it. So this is quite interesting. I didn't actually think we'd encounter maybe this much turbulence today.
Yeah.
So I think all around it's been quite an interesting ascent so far.
Actually, speaking of turbulence, this is presumably the same kind of turbulence that you feel in an aeroplane.
Yeah.
And this is a lot of planes will be flying approximately this height or above this height in the lower stratosphere, won't they?
Yeah.
So is there ever a danger that, or are you ever worried you're going to hit a plane?
So there's been no cases of a radiosonde hitting an aeroplane, or there's been no cases of an aeroplane having to take evasive action, or having damage due to a radiosonde being caught on the wing or anything. So the probabilities of a radiosonde actually either hitting someone on the head when it drops down on a parachute or colliding with an airplane are less than that winning the lottery. So if it did happen, you should have brought lottery tickets. And
congratulations, you
probably have been struck by lightning. So it's such a rarity. I think the only one recorded case was a radiosonde had been launched from one place in America, and it landed in the field site of another radiosonde launching station. And the odds of that, it was ranked like the most unlikely thing on Earth to happen.
I'm just looking at that temperature.
Yeah, so I think we might be hitting the tropopause. It's just starting to kink around. So,
but that looks like that was just it entering the stratosphere.
that is entering the stratosphere.
And that's a really well defined a tropopause.
So that's nice and tidy, and I'm thinking it probably was around 11 to 12 kilometres. So
12 kilometres, yeah, I'll give you that.
We enter a different bit of the atmosphere now, so things we should be on the lookout for, especially the temperature data. If we see little waves in the temperature data, these are inertia gravity waves, which are always present in the lower stratosphere.
I think we might have been optimistic in proclaiming that we hit the stratosphere.
Oh, I'd agree with that because we've got moistures going up to 60%. So that is quite an interesting aspect going on. So
there's a little temperature inversion. Actually, and there was a spike. So that's a temperature inversion at the bottom of the cloud.
So it could be sometimes you do get a very thin layer of cloud against the stratosphere, but this is doing something. So you might actually find this is the tropopause here.
Yeah.
So if there is a cloud at the top, this could be an inversion at the top of it, and also the inversion that starts the.
So could that have been, as you said before, like an anvil, the top of an anvil kind of cloud hit it at the tropopause?
I wouldn't say an anvil from a thundercloud, but just a very stratiform cloud at the top. But as we can see, we're most definitely probably heading into the stratosphere now. The humidity is just dropping.
So that was closer to 13 kilometres actually.
13 kilometres,
very fine.
So if you go down to the tropics, the tropopause won't start to 15 kilometres.
Yeah.
And if you think about it, you've just got warm tropical air. It just takes up more space, just warm air takes up a larger volume than...
And there's also a Coriolis effect, isn't there, with the fact that the Earth's bulging out at the low latitudes. Well, we're not going to reach the stratopause, are we?
No.
So what temperature do you think we'll climb back up to? Minus sort of 30?
So this balloon will probably make it to about 27 to 30 kilometres. And it's around that height, you just start to see the temperature increase going on. It's one of these things when you look at a thing in textbook, right, great, the temperature will increase a bit, but it's actually quite a large distance of atmosphere to go before it starts.
So for a very large distance, it's like the same temperature. What's the fancy word for that? Isotherm.
Isotherm. Yeah. Well, that'd be...
When it's at an isotherm. Just put Google away.
I'm gonna love that when that's edited. Isotherm.
So we're expecting this to basically be isothermal.
Yes.
For quite a while.
But as I was saying, you get gravity waves, and there'll be a slight waveform appear in it. But it's hard to say at the minute. A bit like when we were looking at the inversion down here, it's hard to say because we need to just wait for the. Okay, but looking at the radiosonde,
that's very definitely the stratosphere.
That's very definitely the stratosphere. Yeah.
So what exciting things do we have to look forward to now, or is this sort of the end of the interesting meteorology?
So we're actually still experiencing quite a bit of turbulence with the accelerometer sonde, but the second part of this flight's coming into being now, which is looking for these energetic particles, because we're now at about 100 hectopascals, so the air's a tenth of the density. The cosmic rays are entering the atmosphere, and they're not being stopped by just the density of the air. And so the Geiger counters that are on board will be now doing their job, working out how much cosmic rays actually getting through into the lower atmosphere and not being blocked by maybe the sun. So the sun's at a minimum at the minute, so the amount of solar flares we're expecting is less. So the cosmic ray count is probably going to be higher because there's less interference from the sun.
So how much longer do you expect this to be able to continue for?
So
about 100 pascals now.
So this should it should get up to height-wise. Height-wise, it should get up to about 27 kilometres. So it's got another 10 kilometres to go.
Do they go? Presumably, when they've burst, they don't tend to go laterally too much.
So when they burst, they.
I mean, after they burst, do they just drop like a rock?
When they burst, they drop for a rock for about a kilometre until because obviously in the higher atmosphere, the air is not very dense at all. Yeah. And so the parachute takes a little while to deploy, but then they pretty much follow they literally follow the wind perfectly. They almost sit in the wind.
But that's so well defined. I mean, that's so clearly the troposphere there and the stratosphere. That's really nice to look at.
Yeah. So I think we've got some
Is that a planetary wave? Sorry, inertial gravity wave.
Inertial gravity wave there, potentially. So it's burst now.
Yeah, there it goes. So it's, the pressure's going to rise rapidly.
Yeah, so we're going 12.5.
So is this now going to overplot?
So this will actually just keep plotting this way. So
of course, it's time, yeah.
Get all the descent data. So what we notice is there's been a bit of a jump in the temperature profile. But yeah, because it's so thin up there, it takes a while for the parachute to start deploying and having an effect.
But thank you, Balloon. You've provided us with some valuable science.
Valuable data which be useful to people looking at space weather, people looking at turbulence, and just meteorology
in general. Shotgun not picking it up.
You got a boat?
Thank you, Balloon. You did us proud. Thank you also for making it this far through the video, because my god, I know this is longer than most of the stuff that I make. If you made it this far, well done. The actual launch was like an hour and a half, 2 hours long, so I tried to cram this in and make it as like short and snappy as possible, but yeah, it has to be a certain length. So if you like this though, please do like the video, comment down below that you enjoyed it, because I'd love to do more of this kind of thing. We actually look through stuff in a bit more detail than you'd otherwise get on YouTube. There's also a couple more of videos coming out from my trip to Reading. So Graham, I think in the next one that's coming out, talks about all the different instruments that they have at Reading to look at sort of different variables in the atmosphere, because some of them are really weird, and one of them I wasn't allowed to look at because it would have blown my face off. Seriously. So there's that to look forward to, but do please like and comment if you enjoyed this, because I'd like to make more. Thank you for watching. Thank you to the University of Reading very much for letting me do this and for putting me up and putting up with me. And I'll see you in the next couple of videos. Thanks again for watching.